My name is Dr. G.V. Rao, Professor in the Department of Civil Engineering, Vijnan Institute of Information Technology, Duvada, Visakhapatnam. Today we are going to discuss about pipe flows. Right, before going to discuss about pipe flows, we should know what is the difference between the open channel flow and pipe flow. The water flows without filling the pipe or the flow has a free surface. That means suppose this is open channel, the water is flowing like this is the free surface, and also pipe flow, this is the pipe flow, the water is flowing up to certain level, not fully filled, the water is flowing up to certain level. This is the open channel flow, this is also open channel flow. Open channel flow means that is having free surface. In case of open channels, the flow having free surface. Whereas in case of pipe flow, there is no free surface, the pipe is completely filled with fluid being transported, there is no free surface, right? In case of open channel flow, the flow is having free surface, whereas in case of pipe flow, there is no free surface, the flow is completely filled with the pipe. And second point, pressure at the free surface remains constant with a value of atmospheric pressure. So what is happening? Suppose if the water is flowing through the open channel, that is exposed to atmospheric, that means having free surface. Therefore, the pressure in case of open channel is constant, that is only the atmospheric pressure. Whereas in case of pipe flow, the flow is having or the pressures are varies from point to point, from location to location. The pressures are varies in case of pipe flow, whereas in case of open channel flow, the pressure is constant, that is the atmospheric pressure. And next point, the main driving force in the open channel is gravity. Because of the gravity, the flow in the open channels moving from upper level to lower level. Whereas in case of pipe flow, the flow is moving from one point to another point because of the hydraulic gradient line. Okay. Last point, right, the flow cross-sectional area may be changes. In case of open channel flows, the flow cross-sectional area, this is the open channel, this is the water level, so this is the depth is equal to 1 meter. Another location, the depth varies, this is equal to 2 meters. Right? In case of open channel flow, the flow cross-sectional area changes from point to point because of the depth of flow varies from point to point. Whereas in case of pipe flow, there is no change of cross-sectional area because the flow is moving in the pipe. So, there is no change in the cross-sectional area of the flow because that is the cross-sectional area of the pipe. Generally, the pipes are, the flow is flowing through the circular pipes. Okay, this is the difference between the open channel flow and pipe flow. This is the pipe, varying diameter. Here diameter is different, here diameter is different. Here installed one piezometer like this, one piezometer here, one piezometer here. Right, this is the center line of the pipeline, this is the datum line. Right. In case of pipe flow, already I have explained Bernoulli's equation. Bernoulli's equation states that datum head plus pressure head plus velocity head at one section must be equal to datum head plus pressure head plus velocity head at the another section. Now, in case of pipe flow, there is no free surface, but the water is moving up through the piezometer, so up to the pressure available here. So this is nothing but hydraulic gradient line. Hydraulic gradient line means is the sum of pressure head plus datum head is the hydraulic gradient. This is the hydraulic gradient line. Okay. Whereas in case of open channel flow, this is the bottom of the channel. This is the free surface of the water. Here there is no hydraulic heads, hydraulic gradient line, because the water is exposed to the atmospheric, that is the free surface here. This is pressure head. This is pressure head is nothing but depth of flow in the open channel. This is the datum head. Right? This is the difference between the open channel flow and pipe flow. Right, classification of laminar and turbulent flow in pipes with Reynolds number. This is already I have explained earlier. Once again, the laminar flow and turbulent flow are classified based on the Reynolds number. Reynolds number, you know the formula. Reynolds number Re is equal to rho V d by nu. Rho is the density of the fluid, V is the velocity of flow, d is the diameter of the pipe, mu is the viscosity of the fluid. Based on the given parameters, based on the type of flow, density varies. In case of water, 1000 kg per meter cube, velocity of the flow given, diameter of the pipe given, and viscosity is also given. Then we are going to determine the Reynolds number is equal to 2000 and less than 2000. That calculated value, Reynolds number Re is less than 2000. Based on this formula, the Reynolds number is less than 2000. The flow is known as laminar flow. Some cases, the Reynolds number is more than 2000 and less than 4000. Some cases, the Reynolds number is in between 2000 and 4000. The type of flow is known as transition flow. Some cases, this Reynolds number is more than 4000. Reynolds number is more than 4000. That type of flow is known as turbulent flow. Laminar flow, transition flow, turbulent flow. These three flows are classified based on the Reynolds number. Right here, when a fluid is flowing through the pipe, the fluid experiences some resistance, due to which some of the energy of the fluid is lost. This loss of energy are classified as, suppose the water is flowing through the pipe, because of the resistance between the fluid and boundary, there is some losses. Losses are classified into two ways. One is the major loss, that is the frictional loss, and another one is the minor losses. What is the major loss? Major loss or head loss due to friction. Head loss in a pipe flow system due to viscous effects, due to friction, will be termed as a major loss. Major loss or head loss due to friction is because of the viscous effects. Okay, that is known as head loss due to friction or major loss in case of pipe flows. And another one, minor losses. Minor losses are because of, if the water enter into the pipe, suppose this is the one tank, this is a pipe, this is a pipe, right? This is the water. The minor losses, first one is the because of the entrance to the pipe. This is one region, and another one is the diameter of the pipe expanded or enlarged. This is the another loss. Some cases the diameter of the pipe is contraction takes place here. This is one loss. And also because of the bend of the pipeline and also obstructions in the pipeline, these are the reasons for the minor losses. Minor losses are classified here, that are loss of head due to sudden enlargement, that is the minor loss. Loss of head due to sudden enlargement. This is the pipeline. This is the pipeline. Suddenly the diameter of the pipe increases. This loss at this point, loss is known as sudden enlargement. Loss of head due to sudden enlargement. Loss of head due to sudden contraction. This is the diameter of the pipe that is gradually reduces here. This loss is known as loss of head due to sudden contraction. Another one, loss of head due to exist of the pipe. Loss of head due to entrance of the pipe. This is the, already I have given earlier slide. This is the water stored in the tank. We have constructed one pipe here. The water entering into the pipe, this is one loss that is known as entrance of the pipe, head loss due to entrance of the pipe. And another one is head loss due to exist of the pipe. So this is the one loss, that is the exist of the pipe. And loss of head due to an obstruction in the pipe. This is the pipe flow. We have one obstruction here. This is the direction of flow. So because of this obstruction, we have one head loss, that is the head loss due to obstruction, and head loss due to bend in the pipe, and also head loss in various pipe fittings. But these are the minor losses. Why? Because the loss in this all these cases are very less as compared with the major loss, that is head loss due to friction. Therefore, these losses are known as minor losses. Okay, this is about minor losses, right? Major loss or head loss due to friction. Regarding this, when a fluid is flowing through a pipe, the velocity of liquid layer adjacent to the pipe wall is 0. Suppose this is the one pipe boundary, the liquid is flowing like this, the velocity over the boundary is 0. That means y is equal to 0, u is equal to 0. Away from the boundary, the velocity gradually increases, that already I have explained. This is the another side of the pipeline, this is the maximum velocity, and also this is the right. If the liquid is flowing through the pipe at the boundaries, the velocity u is equal to 0, because y is equal to 0. Therefore, there is a viscous forces between the liquid and the boundary, right? When a fluid is flowing through a pipe, the velocity of the liquid layer adjacent to the wall is 0, right? Second point, the velocity of liquid goes on increases. This is the over the boundary, the velocity u is equal to 0, y is equal to 0. Away from the boundary, the velocity gradually develops and increases, reaches to free stream velocity one location. Okay, the velocity of the liquid goes on increases from the wall, and thus velocity gradient exists. Once the velocity increases like this, here we have the du by dy. Once du by dy exists, automatically shear stress exists. What is the shear stress formula? Tau is equal to mu into du by dy. Du by dy exists because the velocity over the boundary is 0. Away from the boundary or normal to the boundary, the velocity gradually increases, automatically du by dy exists. So du by dy exists, so the shear stress is also exists, right? Right here. Hence the shear stress also produced in the whole liquid due to viscous effects. This viscous action causes a loss of energy. This loss is known as head loss due to friction. Expression for loss of head due to friction in pipe. Now we are going to derive the expression for the loss of head due to friction in the pipe flow. In this regard, we are going to take, right, consider a uniform horizontal pipe having a steady flow in this pipe. That is the first condition. Now, this is the one horizontal pipe. This is section 1-1. This is section 1-1. This is section 2-2. At section 1-1, pressure intensity is P1. At section 1-1, velocity is V1. At section 2-2, opposite to the direction of flow, pressure intensity is P2 and velocity is V2. Okay, now let 1, and 2 are the two sections in the pipe. P1 is the pressure intensity at section 1, V1 is the velocity of flow at section 1, and L is the length between the two sections. This is one section, this is the another section, the distance between these two is L. Okay, that is the length between two sections. D is the diameter of the pipe, because this is the uniform section, D is the diameter of the pipe. And F dash is the frictional resistance per unit wetted area per unit velocity. F dash, this is important term. F dash is the frictional resistance per unit area per unit velocity. Next, HF is the head loss due to friction, and P2 is the pressure intensity at section 2, V2 is the velocity at section 2. These are the terms used regarding the derivation of head loss due to friction based on this horizontal pipe. Now we are going to derive the head loss due to friction. First, apply Bernoulli's equation at section 1 and section 2. This is the diagram. This is section 1, this is section 2. Apply Bernoulli's equation first. What is the Bernoulli's equation? Pressure head plus velocity head plus datum head at one section must be equal to pressure head plus velocity head plus datum head at the another section. That is the Bernoulli's equation. At section 1, pressure head P1 by W plus V1 square by 2G plus Z1 is equal to P2 by W plus V2 square by 2G plus Z2 plus head loss due to friction HF. Right, now we applied Bernoulli's equation at section 1 and section 2. At section 1 pressure head plus velocity head plus datum head is equal to, at section 2 pressure head plus velocity head plus datum head plus head loss due to friction, because the liquid is flowing from section 1 to section 2. Therefore, having the viscosity in the direction of flow, therefore plus HF2. Right here, Z1 is equal to Z2. The pipe is horizontal, therefore Z1 is equal to Z2. And one more condition, the diameter of the pipe is uniform. Automatically D1 is equal to D2, that is equal to D. D1 is equal to D2 is equal, D1 means diameter at section 1, D2 means diameter at section 2, that is equal to D. Automatically V1 is equal to V2 is equal to V. Velocity is also same at section 1 and section 2. V1 is equal to V2. Therefore, Z1 is equal to Z2. This is equal to this one. And also velocity V1 is equal to V2. Therefore, V1 square by 2G is equal to V2 square by 2G. Therefore, P1 by W is equal to P2 by W plus head loss due to friction. Right? Or HF is equal to P1 by W minus P2 by W. This is the equation we have. HF is equal to P1 by W minus P2 by W. This means the pressure head at section 1 is more. The pressure head at section 2 is less as compared with the section 1. The pressure head at section 1 is more, that is equal to P1 by W minus the pressure head at section 2 is less, that is equal to P2 by W. Or from this equation P1 minus P2 is equal to HF into W. W is nothing but what? W is nothing but unit weight of water, or W is nothing but unit weight of water. Unit weight of water W is equal to rho g, mass density into acceleration due to gravity. Therefore, P1 minus P2 is equal to HF into rho g. This is the equation we have. Pressure difference P1 minus flow this is 5 flow, this is section 1 1, this is section 2 2, this is the direction of flow. Here the pressure head is more compared with pressure head at section 2 2. That means the pressure head is reduces from section 1 1 to from section 2 2. Right. Now frictional resistance. What is the frictional resistance here? Frictional resistance equal to frictional resistance per unit wetted area per unit velocity into wetted area into velocity square. Right? Frictional resistance F1 is equal to frictional resistance per unit area per unit velocity, this is denoted by F dash, into wetted area, that is equal to pi d is the wetted perimeter into length. This is the wetted perimeter pi d and length is L into velocity square. Into velocity square, right? Therefore, frictional resistance is equal to F dash into pi d L into V square. Right? Here this is equal to F dash is the frictional resistance into pi d into L into V square. In case of pi d is nothing but P. Pi d is nothing but wetted perimeter. This is the wetted area into velocity square, right? But here F dash is the F dash into pi d is equal to wetted perimeter. Pi d is denoted by P, capital P. Therefore, this is equal to capital P into L into V square. Frictional resistance equal to F dash into P into L into V square. Right? This is the relation. F dash is the frictional resistance per unit area per unit velocity into wetted perimeter into length into velocity square. Forces acting on the section 1 1 and section 2 2. What are the forces acting? What are the forces acting at section 1 1? What are the forces acting at section 2 2? Forces acting on the fluid between the section 1 1 and 2 2. Here three forces. One is pressure force at section 1 1 in the direction of flow. Another one is the pressure force at section 2 2 opposite to the direction of flow. Another one is the frictional force that is also opposite to the direction of flow. Right? Pressure force at section 1 1. Any pressure force, any force is equal to stress into area. Right? Pressure force at section 1 1 is equal to intensity of pressure is denoted by P into cross sectional area A. Okay, P1 at section 1 1 and pressure force at section 2 2 is equal to intensity of pressure P2 into cross sectional area A. And another one, frictional resistance. Frictional resistance F1 is equal to, already I have derived, that is equal to F dash into wetted perimeter into L into V square. Three forces. One is pressure force in the direction of flow at section 1 1. Another one is the pressure force opposite to the direction of flow at section 2 2. And another one is the frictional resistance. These are the forces acting on the fluid element. Like here, this is the pressure force. This is the pressure force at section 1 1. Pressure force at section 1 1. Pressure force at section 2 2. And frictional resistance. Right now the flow is steady and uniform. There is no acceleration. Therefore, the resultant of all these forces must be equal to 0. Right here, P1 into A, this is direction of flow, pressure force at section 1 1, minus P2 into A, that the pressure force opposite to the direction of flow, minus frictional resistance F dash into wetted perimeter into L into V square. This is equal to 0. Now, P1 minus P2 into A minus F dash into wetted perimeter into L into V square is equal to 0. Now, move that side, that is equal to P1 minus P2 into A is equal to F dash into P into L into V square. Right? Now P1 minus P2 P1 minus P2 is equal to F dash into wetted perimeter P into L into V square divided by A. Right. What we have, P1 minus P2 is equal to F dash into P into, that is the wetted perimeter, into L into velocity square divided by A. But we have one formula, P1 minus P2, that is already P2 is equal to HF into rho g. Rho is the mass density of the fluid, g is the acceleration due to gravity, HF is the head loss due to friction, right?